Hello and welcome to Pendower Beach down on the Roseland Peninsula. I've come here today because it's one of my absolute favourites. Geologically speaking, this is absolutely fantastic. There's so much stuff here to talk about. One of the main things is it actually uncovers this turbulent tectonic history of Cornwall. As you do a traverse along the beach here from Pendower Beach, which is where we are here, towards Carne and on to Nare Head, you're effectively doing a transect through what we call an accretionary prism. But critically, these things occur in between two colliding tectonic plates. Because right here, 360 million years ago, we had two colliding tectonic plates, one subducting down below the other one. And in between, you get sedimentary rocks formed that are indicative of quite turbulent seismic activity. So lots of kind of avalanches of sand and huge clasts, and then they're subsequently buried as thrust faults propagate over the top of them as one plate sinks down below the other. And just offshore here we have a dashed line in my mind, and this is a boundary between two old tectonic plates that collided together about 360 million years ago to create what we know as the Variscan orogeny, Variscan mountain chain. So let's have a talk through this transect, this tectonic transect, if you like, through this accretionary prism. It's best observed if you look at a British Geological Survey map of the area. And what you can actually see are these kind of bands of colours, and these different colours represent different geological units or stratigraphical units. And the boundaries between these units, if you observe the map, a lot of them are actually thrust faults, where ones have been faulted up and on top of the other. And usually in those instances, you have older rocks then dumped on top of younger rocks, so kind of inversing the stratigraphy, if you like. And if we start with the far west of the beach, so you come down onto the beach of Pendower, and if you look to the right or west, if you're going that way, you move on to the Port Scatho Formation. Port Scatho Formation is about 380 million years old. It's mainly made up of sandstones with some mudstones. And these are turbidite sequences. They form from kind of submarine avalanches of sediment. Again, where they deposit, they form these kind of lovely beds of sandstone. Then as you kind of work your way eastwards along the beach, you go across a valley. And as a geologist, you often look at geomorphological features, the shape of the land, as to try and understand what's controlling that in the geology beneath. And what we know is controlling that valley is a major fault zone, and we've now called that the Varian thrust. And the Varian thrust has effectively taken older units, these rocks that we're stood on here, part of the Pendower Formation. These formed about 390 million years ago, and these have been thrust on top of the younger rocks of the Port Scatho Formation to the west. These rocks are very different, whereas the sedimentary rocks in the Port Scatho Formation are formed from turbidite sequences indicative of maybe quite high seismic activity, something giving a trigger to cause these sediment gravity flows to take off on these submarine continental slopes. Whereas the rocks here are predominantly mudstone, and within them as well we actually see radiolarian cherts, which form from dead microscopic organisms that have floated to the bottom of the ocean, things that form over tens of thousands of years. These are very low energy environments with very little sediment input, a completely different environmental setting to the Port Scatho Formation. And these probably formed before the onset of these colliding plates in a very settled ocean basin that was slowly being pulled apart. And these have subsequently been pushed together, squished up, thrust and picked and dumped on top of these younger rocks to the west. Working further around the bay, we actually then cross into what's known as the Carne Formation, similar to the Port Scatho Formation, that we see this transition from the Pendower into more sand-rich units, probably from this input of clastic sediments as you start to then get these plates moving together. And then it gets really interesting because we move into a geological unit we call the Roseland Formation. And the Roseland Formation is what's known as an olistostrome or melange, these big, complicated geological words. To put into layman's terms, it's a mess, okay? What you've got is two colliding tectonic plates, hugely seismically active area. And what's this kicking off is not just sediment flows in terms of sand and mud kicking off and floating down the continental slope, but actually much bigger boulders kind of break off and roll down as well. And these are all incorporated into this unit. This Roseland breccia formation, the word breccia means this kind of chaotic mixture of mud and sand and bigger clasts. But some of these clasts can be meters, tens of meters, hundreds of meters, possibly even kilometers in size. And this has all been kicked off. There must have been some biblical tsunamis when earthquakes trigger these huge landslides and what are known as glide blocks down. And as we actually continue round Garons Bay to the furthest east of Garons Bay, which is Nare Head, Nare Head is about kind of a kilometre squared bit of land which is made up of basalt. So these are submarine basalts. We know that because within them we see pillow lavas, which are these kind of tubes of lava that get erupted onto the sea floor, and they create these lovely little kind of pillow shapes. So we know they're submarine basalts, but it's out of place. It shouldn't be here. It's kind of resting on top of the Roseland breccia formation, but we can't quite see any faulted contacts between the two. So one theory is that this is actually one massive glide block, that an earthquake during this kind of subduction, this onset of continental collision, caused this huge fragment of the sea floor to slip and slide down in during an earthquake. And again, the tsunami that would have caused is just hard to fathom. So absolutely incredible geology we've got here. To work through this section is effectively doing what's going on in the equivalent of walking from the Andes into the Pacific Ocean now, or on the east coast of Japan, and the Marianas Trench and things like that, where you've got subducting plates going on. It's absolutely incredible, and I do implore that you do some more reading up on this. It's amazing.